Okay, I've just hit record, so we're going to get started. Good morning, everyone, and welcome to the spring edition of Trainee Talks. Trainee Talks is a monthly webinar series showcasing the research topics of our CREATE graduate students in their area of interest related to software engineering and AI. My name is Aurel Ikama, and I'm the program coordinator for CREATE at Concordia University, and I'll be moderating the webinar today. So this morning, we are very pleased to introduce two PhD students from our program, Adekunle and Aurel, as they share their research with our group. Adekunle Ajibode is a PhD student in computer science at Queen's University, a member of the SAIL MCSI lab, and a student member of IEEE. His research focuses on improving the release process of large language models by analyzing software and model repositories. Adekunle will be presenting his work on Towards Semantic Versioning of Open Pre-trained Language Model Releases on Hugging Face, which was recently published in the MC Journal. Immediately following, we will have Aurel Ikama Honey. Aurel is a PhD student at Polytechnique Montréal under the supervision of Professor Foods-Com. He also works in collaboration with the National Bank as a technical lead in software quality. His fields of research are software quality and AI. And Aurel will be presenting the preliminary results of his work on a comparative study of LLM architectures for root cause analysis in end-to-end test logs. Each trainee will speak for 20 minutes, followed by a 10-minute Q&A. This webinar is being recorded and will be available to view on our CREATE website at se4ai.org and also on our YouTube channel. So with that introduction, I'm pleased to turn things over to Adekunle. Adekunle, take it away.
Okay, thank you very much. Let me quickly share my screen. Okay. Thank you once again. My name is Adekunle Ajibode, and I'm a PhD student at Queen's University, and I'll be presenting our current recent published paper titled Towards Semantic Versioning of Open Pre-trained Language Model Releases on Hugging Face. Just as I love football, I play football, so just as football has already, it's bringing together different people from different perspectives, level, different tribe and different countries. Is this model is bringing different developers, different companies together, and they are now plugging into Hugging Face to take different models in order to integrate into their workflow. So this is why, even with that, we can understand that there is no how all these models, the way they are being released on Hugging Face, are not without any issue. So okay, sorry, let me make it a presentation. Okay, thank you. So we see that when we go to Hugging Face, we make different companies will be there to, or an individual as well, take these models and integrate them into their workflow, whether for different purposes or whatsoever. And majority of these, the usage of these models are basically the NLP models, are the more prevalent models that have been integrated so far based on the recent work. But this model cannot come without any issue, because when we go to Hugging Face now, you will see that if you want to select a model on Hugging Face, you have to check the name first. There are different names on Hugging Face, given to these models on Hugging Face, and these names have different segments. These segments have different meaning. For example, this is a name. This is a name of a model. It has base model, it has language, it has variant type, and it also has an identifier, also version. Another name, you see this one is only just one, Emorobata, is just an identifier. Another one where you see that it has just base model, it has an identifier as well. Another one, you see that it has just description. Another one, you see Galactica this, it has identifier, and it also has size. Now, this model, we can see that there are different names when these are naming conventions like base model, language, variant, identifier version. These are, we call this naming convention. It has 5 different segments. This one also has only identifier. I mean, it has only identifier, the Emorobata. Other ones have base model identifier. So these are different naming convention on Hugging Face. And we have the same thing as version and variant inconsistencies too. Like if you see some names, they have V1, like what the normal convention in software development when they are naming they are giving the version, you see V1 and you see V2 as well from the same person. However, if you go to another repository, you see V0.1 and you see another one 0.2. Now, the problem here is this, sorry, I can't see this. Wow. Sorry, I mistaken. I don't know if I'm still sharing this something. Can you see my screen?
Yes, everything looks good to me.
Okay, but it's showing a different thing here. Sorry, I'll stop sharing and I will share, please.
Okay.
Okay, so sorry for that. So now we have the versioning here. It has version 1, the other one has version 2. This second one has version 0.1, the other one has version 0.2. We can see that there is an inconsistency here using different identifiers so far. And when we are talking about the variant types, some of them use FT, which means fine tuning, and some of them do not even use anything. So, like this one now that says this still bad based on case commit label, we cannot understand and we do not even know whether the model is a fine tune model or it is a dedupe model or any type of model it is. So these are the kind of inconsistencies on Hugging Face that we are trying to explore. As a result, we answer 3 research questions. And the first one is, what are the current naming and versioning practices of pre-trained language model on Hugging Face? And the second one is about what are the PTM variant types and how their qualities in terms of reproducibility and transparency on Hugging Face. Now, the third question is, to what extent do versioning identifiers in PTLM names align with the actual changes in the PTLM versions on Hugging Face? In order to explore that, we iterated through the following. So we extracted model from Hugging Face. We extracted 196 models, 196,201 models from NLP models on Hugging Face anyway. So in the step 2, we identified those ones with the base model, that is those ones that identify their base model, the starting point of their model. Now, in the third phase, we filter out models that is less than 1 million parameters because we are dealing with models with higher parameters. Now, which constituted this 52,227 models constitute our exploration, our main data set. So in the entire data set, we use the entire data set to explore the versioning practices, the hidden version in the PTLM repository commit. Now, we also did some manual work, like we manually sampled 384 models from the sample of 52,227. So we use this random sample to explore the naming convention because it's the manual work. So this is what we use to answer the research question 1. So going forward, For the RQ2, we use the entire data set as well to explore the prevalence, the reproducibility, and we automatically analyze the release transparency. Now, we also did randomly selected 377 models. Then we use that one for release transparency as well. Now, we use it to answer the RQ2. So for the RQ3, we identified models that indicated version in their names, that's V1, V2, something in their names, which are 3,471. So we randomly selected 518, which we now use to answer the mapping of the predecessor and successor version. We use it to identify the changes that is being made in the major and minor, and we also find the difference between the major and minor version of the model. Now we use this to answer our RQ3, which says what changes occur in between different versions of a PTLM on Hugging Face. Now to the results, we identify 12 different segment types on Hugging Face. Like we have identifier-based model and size and all those stuff. Meanwhile, identifier constitutes 70.8% of our studied data set. Base model constitutes 39.8%, and the size constitutes 34.3%. And furthermore, we now discover that, okay, on this, which of these segments is more correlated with the higher download? We discovered that model mentioning model size actually have more downloads on average than those that mention other segments. So we also identify 148 naming conventions on Hugging Face, in which the very top three are the identifiers and size, and those that mention base model and identifier as well. Now, after that, we discovered that there is no significant difference between the length of the name and the download rates. No matter how, maybe even if it has 50 or 100, we identified that there is no much significant difference between the length of the name and the downloads. However, we identified that the model name that constitutes identifier, base model, and size is more associated with higher download rates. That is 1,072.12 on average per model. So as a result, at the end, we recommended that if a model name can be this concise, it is more appealing to the users. So furthermore, we identified that fewer models indicate versions in the name. The reason we explore this is that we discovered that there are changes in the model weights of these models. There are changes, but since there are changes, we expected the name of each of these models to have version, but they are just changing the model weight without indicating them in the name, since name is the only place that we can indicate the version of a model on Hugging Face. There is no special place to indicate version. As a result, from these 52,000 models, only 3,000, that is 6.64, indicated version in their names. So furthermore, from these 3,471, only 67% are major versions, while the rest are minor versions. That is, the remaining 33% are minor versions. As we can see here, we see that a total of 1,282,874 changes were observed in their model weights. However, we can only see 52,000 models. That means if all the changes in the model weight are to be regarded as versions, we will have like 1,282 versions of model. So instead of this 52,227 models. Unfortunately, we see that frequent changes, that is a total of 524,419 changes, were made in the model files. Since we categorize all the files into five: model file, data and configuration file, other file, documentation files, and code files. But we discovered that 40.878 changes were made in the models file. So we now explore further which of these which file are they using for the model file. We identify security-based one, which is tensor. We identify generic and binary file. They use PyTorch to save the model. They use ONNX. They use TensorFlow model file. They use TensorFlow Lite, and they use Apple Core as well. Meanwhile, there are 62.663 of 524,419 changes were identified from TensorFlow file. That means that TensorFlow file is the most used method of saving the model weight. Furthermore, we identified 299 base models during the course of this exploration. These 299 were derived from the 52,000 models. The top ones are Llama, BAT, Mistral, and Distill-BAT. So based on the age of this model, the time they were being published, we see that Gemma, Mistral, and Llama are the most prevalent, instead of Llama, BAT, and Mistral that we identified initially. So we identify 4 variant types for PTLMs. Variant types of PTLM, they are denoted in the name and the model name, in the configuration file, and in the tags. 70.72 of 52,000 plus models does not state their variant types. That is, we do not know the method of their reusable, whether it is fine-tuned model or it is distill model or whatsoever. We do not understand. It's only less than 30% of them indicated their variant type. And this variant type were consolidated. We identified 14 different indicators. Some of them use FT, some of them use integer 4, some of them use deduped. However, we consolidated them into 4, that is quantized model, fine-tuned model, distilled model, and deduped model. Therefore, quantized model and fine-tuned model are the most prevalent variant type, as we can see in the figure. The PTLMs lack training data sets. We discovered that from the 52,000 plus, only 33,000 plus model have metadata. Metadata means that there is a special place for data sets. They have that. 65% of the models have this place where we save the training data set. We indicate the training data set. However, only 8,000 of them indicated the training data set per se. They have the metadata, but they didn't specify the training data set that was used for training. It's only 24% of them that did such. And from this, we now perform manual analysis, and we discovered that from the remaining one, that is 25,000 plus, only 12 of them mentioned the training data set elsewhere, whether in the model card or somewhere else. So as we can see in the figure, these two models have more training data sets, but this is not statistically significant. And the chi-square also shows that fine-tune, distill, and quantized model, they release they tend to release the model, data set with their model. And we also discovered that majority of this model have a model card. They are 33% of the 52 LLM do not contain model card. That means that 67% have model card, which is more than the existing one. In the previous work, I think it's only 62% that had model card in their paper, but here that means there is an improvement in the releasing of model card. We also see that the duplicated model have the higher percentage of model card. Also, the chi-square shows that they are fine-tuned and quantized model. There is a statistical significance between the PTLM versus the model card. That is the fine-tuned model, they tends to release their model card. Likewise, the quantized model too. We also discovered that PTLM generally lack predecessor and successor version. What I meant by the predecessor and successor version is that you have version 2. Where is your version 1? We were unable to detect your version 1. Okay, you have version 2. Where is your version 3? That's the successor. We were unable to get version 3, but you have version 4. So we see that majority love 57% of 330 major versions and 65% of 288 minor versions sample lack predecessor versions. They don't have whether the previous one or this the next one. And model card changes that it most occur between versions in 71% in major and 80% in minor. Also, significant difference between major and minor version also appear only in base model and in model weight files. Also, there are generally 28 different changes. Yes, we identified 28 different changes in PTLM, and major versions have 28 distinct changes. Minor versions have 8 changes. So we now consolidated this into 9 different categories. Sorry for this. I think this one looks blurred, but I'm thinking of a way to make it bigger, but there is no space. So we consolidated them into configuration changes, model architecture, license change, performance change, dataset change. We have the training library change, and we have energy consumption change, we have performance metric change, and we have other changes as well. Now, we discovered that only configuration and license changes are statistically significant between major and minor version. That means that the changes being made between the supposed major version and supposed minor version are not different. They are all the same. They are making the same thing. There is no changes. It's either they are just changing the name or they are just changing the data set or whatsoever. But we discovered that the changes are not statistically significant. Now, last but not the least, we discovered that there are some changes when made in a particular model. They made another the same change in another aspect of the PTLM. For example, we discovered that when they change evaluation metrics, they also change the data sets, because there is an association between them. When they change the training library as well, they also change the performance. The performance of the model also changes. When they change the model architecture, and they also change the configuration of the model. That is why we observe a strong association between them. Yeah, thank you. And in summary, we identify 148 distinct naming convention, and we also identify 14 distinct variant type, which we consolidated into 4. That is quantized, fine-tuned, and distilled and dedupe. We also identify 28 distinct changes in minor version and 28 changes in major version, 8 changes in minor versions, and we consolidated the changes into 9 categories. Thank you.
Thank you, Adekunle. Does anyone have any questions? We have some time for a couple of questions before we proceed to the next speaker. Hassan, please go ahead.
So thank you for the presentation. My question is, so we have 148 different naming conventions. So what is your recommendation here?
Yes.
Did we just go with one, or there are several of them that can be suitable for different scenarios? What do you recommend at the end of the day?
All right, thank you very much. At the end of the day, we were only able to recommend the one with the highest downloads, because since we have some, when they specify size, there are more downloads with models with size that specify size. So base model as well, and the identifier. As a result, in order to have a concise one, what we recommended is to have base model, the identifier, the base model, and the size, since that correlates with higher downloads.
But my follow-up question is, just because a model is being downloaded more, does it really mean that the naming convention is the best? Was it because of the naming convention that it was downloaded the most, or just because it was a very popular model that everyone knew about and don't care about the identifier, basically? I mean, the naming convention, they just downloaded. Have you found a way to cross-check this? Is it the download or is it
Yes.
the name?
Yes, I think it's because of the download. The reason is this: we correlated we checked the statistical significance between the length of the name, and the download rate. We see that when they have two, there is no, even the length of the name does not have any relationship with the downloads. So as such, since we are only able to see that, okay, this one has more downloads than the other, and it is not about how popular the model is, but just the name. Since we do not have only one model, it has a lot of model, maybe 30, 40, we in that range. So that means it could be the segment that is being identified, like the base model, the identifier base model, and the size.
Okay, great. And one last question. So besides just checking the name, have you also investigated maybe the model description? Maybe those that have, a smaller name, maybe they have a more complete description about the
Yes,
details of the model?
in the model card, right? Yes, since actually we did not check whether the description is complete or not completed, because there is an existing paper that did something like that. There is checking the completeness of the model cards. So redoing the same kind of thing is like repeating what has been done in the literature. We only check the model card of the major version, the model card of the minor version, if there is any difference between them. So we calculated the percentage of the difference, and we see that there is no difference between. They just switch the model card, put the first one, put it in the second one. They just change the name.
Okay, great. Thank you.
You're welcome.
Okay, Samuel, please go ahead with your question. Samuel, you have to
Sorry.
yourself.
Okay, yes. Thank you, Adekunle, for the nice presentation. My question somehow is a bit of a follow-up, but not a follow-up. So you mentioned that in the end you made recommendations based on the models that have the highest number of downloads in response to Hassan's question. My question is more to find out about your target group when you began the research. Was your target group the users of the model on Hugging Face, or developers who are posting their model on Hugging Face? I just want to, if you can clarify the target group.
There are three. First, the Hugging Face administrator. Recommending a kind of we were trying to see if we can propose something for them that may just pick a name or give them a kind of instruction on how to label. There is no tutorial, to be sincere, on naming your model. If they can come up with a kind of tutorial on how to name their model in order to reduce the inconsistencies, that is for the administrators. And they can also provide a mechanism for giving names to the model. When they are able to do that, I foresee that it is doable by the time you just give some mechanism like picking a name, I don't know, creating some command. Okay, the user, the identifier, the size, and the base model. If they compulsory something like that for all the users, I mean all the practitioners, I think that can help a lot to reduce the inconsistencies instead of having long, because I see a name with like 20 segments. You can imagine you want to name it 20 segments, that is a lot. So if they are able to come with something like that to reduce the inconsistencies, that is from the administrator. For the practitioner perspective, yes, it is not mandatory for them. They are not mandated to use, I mean, they are not constrained to a specific name. They are not constrained to, because this is an open source. They are just helping. But it will be good if they are concise in their naming convention. Seeing that you are having almost 20 segments in your name, that is too much. So it will help them to come up with, by the time we gave them this kind of concise name, they will be able to come up with, okay, let us put this. Whenever you are giving a name to your model, you can give it maybe base model, training mechanism, or anything, but not more than 5. So we can recommend something like that. For the users, we believe that checking names is not synonymous to getting the best models. So we only recommended for the users to go through, not checking only the name, but go through the model cards to see what is in there. Actually, my next target is to work with one of the Hugging Face personnel to make some findings and to see if there is a way we can help in this naming and versioning convention of these models and where we can help the users more. So that is our target.
Okay, all right. Thank you very much. But just to clarify, just because you're contributing to open source doesn't mean you are at liberty to do whatever like you want to do. You mentioned something like because the practitioners are contributing, they don't have any restrictions. Even in like open source projects on GitHub, they have some restrictions. Otherwise, your contribution will be rejected. So just to clarify.
All right, thank you.
Thank you very much, Adekunle. We're going to have to cut it off there, but thank you for your presentation and congratulations again on your paper publication.
Yeah, thank you.
So we're going to turn things over to Aurel next.
Yep. You see my screen?
Yeah.
Looks good.
Okay. Good morning, everyone. My name is Aurel Ikama, and I am student in Ph.D. In Polytechnique Montréal. So I will talk today. Today I will talk about my current work. So the subject is a comparative study of LLM models for root cause analysis on end-to-end test log. So the agenda is first we will talk about the industrial and academic context. After that, I will mention some related work and different axes that I focus my state of art. Then I will present my approach design and the preliminary result and future work and conclusion. So let's begin with some definition. So in this work, end-to-end testing means end-to-end integration and user interface testing. So it's a kind of test that we can use to test API or user interface, especially in web application. The second definition is about root cause analysis. So root cause analysis in this work is a structured investigation that aims to identify the truth cause of problems. So we will limited the work on this definition. So currently, I work in collaboration with National Bank. So we noticed that there are 10K run per week of bot of automation test, and the pass rate is around 50. So if we if we assume only 10% failure, we have 1,000 tests to maintain. So if we assume that the maintain of test is estimated at 3 hours on average, that is 3,000 hours of maintain that the team need to put each week to maintain the 10% fail. So it's a lot of time, and teams don't have this time to maintain fail. So that is why we therefore want to have a maintained support solution to see redundancy or even feature with a large impact. So we need to have a tools that can define what is the root cause of a test and cluster this root cause in a set of root cause to help teams to maintain test. And we have another problem in academic context. End-to-end test is typically proprietary data. So each company have its own automation test, and they don't publish in GitHub, for example, the use case or the automation test. So we don't have any papers in the academia focus on end-to-end log analysis test. So that is why we try to propose tools that can analyze and provide the root cause of this kind of test. So the related work, we have three axes. We see three axes in current papers in academic context. So we have root cause analysis axis, and we have some papers and some tools that can use or know LLM to define root cause analysis. And we have also a lot of paper about unit tests because we can have, I think, we can have a lot of data in GitHub about unit tests. So we have a lot of analysis about unit tests, and the last axis is about anomaly detection using AI. So we have also a lot of papers based on AI that use LLM or CNN to define what is the anomaly based on log. But the problematic here is we don't have tools that can help to decision of uh, software engineer or test engineer to decide what is the kind of fail, what is the root cause of fail uh, based on AI and logs. So um, that is the overview of my approach. So the approach, it first of all, we need to collect logs. So the step can be depend um, to the infrastructure of the company that we need to collect data. We have after that a log presentation and log labeling. Um, then we have event correlation analysis use with LLM. So this step will produce IST of um, root cause or of cause of fail of the test. After that, we have root cause identification and answer. So let's talk about log collection and log representation and labeling. So automation test is a kind of bot that we can use to test the system. So here in this presentation, we have here a bot that we can use to test any system, and this bot generate logs. So this log is our input uh, for our analyze. Uh, we create for the first step, we create a code that can extract a template based on level and um, structure of logs. So this code will create a template, and in labeling step, a software development engineer in test in a national bank will labeling this template. So we can see here one example of template. So we have here a log file, a raw log file, and after extraction of template, we will have a JSON file with some data of the error. So we have level of error. We have a message, the time, and the position in the log. We can have also parameters if in message we have some information, some specific information. And here we have an example label that the test engineer can put. So for the data set, we base our work on 5 national bank end-to-end automation project. So currently we have only 20 logs file labeled, and we are working to try to, it's a manual activity, so had to have time to have engineer for the labeling step. So we have um, 1008 logs that we collect. So we will try to labeling all data that we collect. So sorry. For the LLM models, we we use locally because we have some we use Olama, and we download locally for 5 model of LLM to compare um, the result of each. So we uh, so for the methodology, we start naively to collect logs and put it in LLM models with a prompt to um, so if this model can answer a good label. So it's not a good approach because we can have some, it depends of log size and LLM model configurations. So we have one verbose explanation of uh, large large amount text in a log. And in this approach, we can have also noise because in log we can have some information, some debug information, or um, a lot of verbose information that we want. Um, So the question here is, which methodology offer the best performance for identify root cause of end-to-end automated end-to-end automated test? So secondly, we try to generate a template and use a template with a prompt and put it in a LLM model to see um, and we see that we have answer, but the accuracy is low. So we can see here with Llama 3.2, we have this performance. And we can see also systematically when we have Chrome driver root cause um, in true label, the LLM predict Jira import issue. So we have here, I think, um, uh, we have a problem because the model here can the model he can uh, detect only Jira import issue, and it's not the root cause, but the second cause uh, caused by Chrome driver issue. So we try to add one more LLM model with event correlation analysis. So we use the same prompt with the same template and put it in this event correlation model. And after that, we the output of event correlation model is IST and a prompt that we defined before in a root cause analysis model and see which kind of answer we can have. So in this case, we have a good accuracy. So we use Llama with 20 logs files. So we don't have enough data, but we can see we have one accuracy and the performance is very good. So we can see also here with Llama 3.2, the Jira import root cause is identified and the Chrome driver root cause also is identified correctly. So in the second question, we need to see which LLM model offer the best performance for identifying root cause of end-to-end automated tests based on her 20, 20 log file. So we have some preliminary result. We can see here Llama 3.2 have a good result. We can see also that reasoning model like DeepSeek-1 have 0 because the model try to explain more and put more explanation, not the exact label that we need. So we will work to try to extract some information about label to increase this performance. And we can see also that model like Mistral have a low accuracy and geometry have some medium accuracy like that. We can see also that we have for inference time inference time max per log file can be high, so 1 minute. And if we have more than 1,000 file log, we can have it can take a lot of time. So in the future work, we need to try RAG. So we need to add a RAG, so embedding log and try to store prior analysis to element the context of current analysis. So the goal is to see if prior analysis can increase the result of root cause analysis. And we need also to see how does the chosen methodology perform in the face of noise and incomplete test log for root cause identification. So in the conclusion, event correlation analysis adds analysis that significantly helps in identification in identifying root cause, and even with an older LLM like Llama 3.2, you can achieve significantly good result. And my model also use only 3 billion of parameters. So it's a good, we can have a good and significant result with a small LLM model. We need to replicate the experience on more data to identify the limitation of our approach. So thank you. That's it one.
You Aurel. Dr. Adams, please go ahead.
Right, yeah, thanks for presentation. So I wonder, like you said that the results were lower than you've expected. I wonder, does it have to do with, like, with the log files? You often have like abbreviations. You often have like kind of weird kind of letters or kind of signs and stuff like that, or kind of, I don't know, kind of characters to indicate some things are in the same conversation, others are in different. Did you look into that?
Which can okay. You said a character in a log file, right?
Sorry, can you say it again?
You said a character in a log file.
Yes, yeah. So in the log file, I mean, so they have abbreviations, typos. You have also sometimes, in my own log files, I kind of, if I know certain events, I want to kind of see them as in a certain conversation or a sequence. I put like some characters, so I know that I should look at these lines here. I should ignore the other ones. So there's a lot of kind of semantics in seemingly kind of weird characters or kind of practices in a log, and then an LLM might not by default know those. So you mentioned going to use RAG and these kind of things, but I wonder, before you do RAG, like, is there any kind of filtering or other kind of steps, maybe from existing work on log processing, that you could use?
Okay, so that is a good idea. I didn't think about that. I think we can for the RAG do this analysis, this syntactic analysis before, and yes, it's a good idea. So I can I think add this access in my research.
Oh, great. Thanks.
Oh, sorry, I was on mute. Does anyone have any further questions for Aurel before we wrap things up for today? No? No more questions? Okay, well, if there are no further questions for either speaker, I'd like to thank everybody again for joining. And yeah, thank you to our speakers, Adekunle and Aurel, for your nice presentations. And hopefully you'll be able to take some of the pieces of advice that you received from your talks today and incorporate them into your ongoing research. So thank you very much, everybody, for joining Trainee Talks, and we will see you next time.
Thank you, Lori. Thank you, everyone.
Thank you.
Thank you, everyone. Bye.
Bye-bye.